Welcome to Fresh Thinking by Snowden Uptiro. My name is Susan Havlin. I'm the Managing Consultant for the Geology team in Perth. I'm joined today by Ian Glacken, our Executive Consultant from Perth. Welcome, Ian.
Thank you, Susan. Just one of the executive consultants. Yeah.
One of the important ones. So welcome back. We're doing a series of podcasts on recoverable resources simulation and the future of resource estimation. In the previous episode, we discussed Localised Conditional Simulation, or LCS as we call it, and how it allows information from multiple realisations to be translated into a single practical block model while preserving the grade variability. One of the major advantages of simulation-based approaches is that it also provides new ways to analyse uncertainty and risk within a mineral resource model. Well, not technically new ways, but it allows us to. So in this episode, we'll explore how simulation can help us better understand uncertainty in mineral deposits and why approaches like LCS provide a more consistent framework for that analysis. So one of Ian's favourite topics is uncertainty. So why is uncertainty such an important topic in mineral resource estimation?
Because simply uncertainty is a feature of geology, it's a feature of grades, and we need to capture it. We need to put it up front. We need to communicate it to the engineers, communicate it to the management, and we don't need to hide the fact that we do have uncertainty in grades, particularly in high nugget precious metals, but we have uncertainty to a lesser and greater extent in various deposits. So the essence of this discussion here is that while LCS gives us an estimate, which you talked about in the last episode, it also gives us the very great benefits of having a measure of uncertainty. So that's really what we're talking about here.
Right, and that uncertainty can lead to better decisions on drilling programs, development strategies, risk management, that kind of thing.
Risk qualified decision making is what it's all about, and risk qualified mine planning.
Right. So how does conditional simulation help us understand this uncertainty?
So where we're at with the industry, we're not 100% there. As we've discussed, I think in the industry, we've been able to capture and measure grade uncertainty for 40 years. Where we're at with geological uncertainty is a bit more uncertain because it's more difficult because every ore body is different. So grade uncertainty, we're there. Geological uncertainty, we're not quite there. Although there are an increasing number of case studies where people are looking at geological uncertainty. So as we've discussed, we have a range of realizations. And if we have a low degree of uncertainty, like say a low nugget effect in the variogram, then those realizations will be very similar to each other. If we have a high degree of uncertainty, which we often do, those realizations will be very different to each other. And this uncertainty is simply a case of acknowledging it and attempting to quantify that.
So we can look at that uncertainty based on a domain by domain basis.
Yes,
in this sort of
and I know one technique that you've been looking at is this idea of a local CV. So a local CV would be, if you like, a moving average across panels of the coefficient of variation of the simulations. The coefficient of variation is simply the standard deviation, the variability divided by the E-type or the mean. And that gives us a local measure of variability, which we can get from the simulations, which we can't really and efficiently get from ordinary kriging, say.
Yeah, so you would expect maybe where there's a lot more drilling, maybe your CV should be lower.
Absolutely.
In general terms.
Absolutely, yes, that's right.
So this sort of leads on to my next question is that, can simulation be used to support resource classification?
Certainly can. And for maybe 20 years now, we've had a technique which you might call the 90-15 approach. This was popularized by Harry Parker in the early noughties. And it's a technique that's used by most of the major gold companies, not all of them, but most of them, and certainly the other major companies like Rio Tinto and BHP. So it is a way of building uncertainty into our resource classification. And the way it works is essentially we look at the uncertainty in a block and that block might be 3 months worth of production or annual production, and we look at the relationship between the uncertainty in the block and what we call the 90% confidence interval. The 90% confidence interval essentially means that 90% of the time our grades are going to be within X and Y. And what we say basically is if that 90% confidence interval is less than the grade plus or minus 15%, in other words, 15% error, then we would allocate that block to a higher category. So essentially what we're doing is we're building uncertainty. Now, where does the uncertainty come from? Well, you can play around with the kriging variance, which can be done, has been done, is being done, or you can use simulation, which is what we're talking about. And of course, while we're generating these simulations for the LCS approach, we've got the ability to use the suite of realizations for our classification.
Right. So basically, there's multi uses for all these simulations, not just getting one, grade per block, but also helping to inform us for our classification and our uncertainty around the whole estimate, really.
Yeah, that's right. I mean, I always tell the story every 3 years. There's a Geostats Congress, which is like an international geostatistical catch-up, and it goes for 2 or 3 days, and there might be sort of 200 or 300 papers presented. And of those papers, maybe 10% would be on estimation and 80 or 90% would be on simulation. In other words, the capturing of uncertainty. At the last resource estimation conference, which was held in Perth last year, Clayton Deutsch, who was my old professor and has just retired, a professor at the University of Alberta, he gave a very provocative keynote address, which basically said that as a geologist, our obligation is to communicate uncertainty. So he's basically saying, well, we've got this uncertainty, we can measure it, let's talk about it. So that's
I do believe he also said that okay was not okay.
Well, that's right, he did say that, yes, yes.
So one thing I do get asked is, could we use these simulations used to evaluate the probability of achieving certain grades or cutoff grades? Because that's obviously a big question, right?
Absolutely. If we have 100 realizations or 50 realizations, we can average them over a particular block size, and that block size might represent quarterly production, it might represent a stope, it might represent the bench, and there's a number of things we can do. Quite simply, we can look at the number of realizations where the grade is above a cutoff, and that gives us the probability of exceeding or not exceeding that cutoff. So that's a very common application of simulation. And as we've discussed with our LCS approach that we're talking about, we're getting a grade estimate through localization, but we're also getting that suite of realizations. So we can say, for instance, within a particular stope that we're going to mine in Q3 2026, what's the probability that we're going to achieve a 3 grams per ton head grade, based on our simulations. We can look at the upside and the downside of the grades for a bench, So there's many, many applications of this, which can only enhance our mine planning process.
Can we not generate uncertainty in an ordinary Kriging model?
Yes and no. We do get a measure from ordinary kriging, as everybody knows, called the kriging variance. Kriging variance is a mathematical minimization of the error between the unknown true grade and the actual estimated grade. So it's a proxy for uncertainty, but it's not as good or as complete or as comprehensive as generating a whole series of realizations. So while people have used the kriging variance or the kriging error as a measure of relative uncertainty, it's not so good. And one of the reasons it's not so good is that when we're averaging blocks, we have this smoothing effect, which we talked about in ordinary kriging. And sometimes we have this idea of over-smoothing or conditional bias. So any uncertainty based on a kriging technique is not likely to be as accurate as a simulation technique. So in other words, if we just use kriging, we're evaluating the variability about a model that may not represent the true variability in the deposit. In other words, we might be understating the variability.
All right, so this is how LCS improves that situation. So you're able to keep that variability and therefore predict the uncertainty with more confidence.
That's right. We're generating the E-type estimate or the SMU estimate by localizing the simulations at the estimated grade. So we're getting a estimate that sits within the range of realizations. So that's the first thing. So that we have our band of realizations, our simulations. The LCS tonnage grade curve sits in the middle, and then we have the uncertainty around that. So the key point here is that the uncertainty, the LCS estimate sits within the band of uncertainty. One thing that if you've done, I know you've done this and I've done this, if you do a set of simulations and you take the E-type, the average, you'll find that the tonnage grade curve is smoothed because it represents effectively the ordinary Krieg estimate.
Yeah.
And the range of simulations doesn't sit around the single estimate. So one of the great advantages of LCS is that the LCS tonnage grade curve sits right in the middle or sits within the range of realizations, and that's really important.
Yeah, so in a test that we did complete, we did an OK estimate as well as the I think it was 100 simulations, and we plotted out the grade tonnage curve, and that's exactly what we saw. The localized conditional simulation sat right in the middle of the 100 realizations, and then the E-type curve sat below it, and that sat very close to the actual OK grade tonnage curve. So yeah, we've actually proved that in theory.
Yeah, that's good. No, I know that's a case study that you'll be presenting sometime in a paper. But the fact is that the average of the simulations are real. The E-type effectively equates to the ordinary Krieg or the estimated model. In other words, it's occasionally oversmoothed, or it is oversmoothed.
Yeah.
Whereas the LCS approach gives us, as I just said, gives us a tonnage grade curve that sits within the suite of realizations.
Yeah, which is essentially why we don't report the E-type, because it is.
That's right.
It is smoothing the variability.
Yeah. So that's an important point. The LCS estimate is not the E-type
Yeah.
of the simulations. It uses this idea of the E-type to rank the grades. Yeah, so the localization approach uses the E-type, which is the average within an SMU, and then those SMUs are ranked, and the local grade is generated on the ranking estimate, and the method. One of the outcomes of the method is that the tonnage grade curve sits within the range of those realizations, not outside of it as the E-type would.
Yeah. So the actual LCS process and what it produces, that actually really matters in decision making. So why does this matter for decision making?
Well, you want to have the uncertainty pegged to the estimate, and with the LCS approach, the uncertainty sits around the estimate, not necessarily symmetrically around the estimate, but it sits there. The uncertainty is not separate from the estimate. The estimate is included in the band of uncertainty, and that's really important because we can take the LCS approach, which gives us the estimate that we would use for mine planning or for cash flow analysis, but then we can generate that uncertainty in the knowledge that that band of uncertainty sits either side of the single estimate there.
Yeah. All right. Thank you, Ian. So in this episode, we've explored how conditional simulation and LCS can provide a more consistent framework for analysing uncertainty or risk within resource models. In the next model, we'll shift our focus to the mine planning implications of these models and look at how more realistic representation of the variability can influence decisions around selectivity, scheduling, and mine design. Thank you, Ian, for joining us for this episode.
Thank you, Susan.
Thank you for listening to this episode of Fresh Thinking by Snowden Optiro. If you enjoyed this episode, please subscribe. And if you'd like to listen to more, you can find it where all good podcasts are found and on our YouTube channel.